Hey everybody, Dr. Retzik here with you. This is our fourth video in chapter 15, where we start to think about doing double integrals, but not with respect to x and y. This is double integrals in polar coordinates. Let's get started. So here's the idea. Sometimes you'll be integrating over a region in the xy plane where the region is much better described in polar than it is in Cartesian coordinates. So an example of a region that fits that description might be something like this. That's good old xy plane. This is not a 3D picture, but rather a 2D picture where the region is happening between a couple theta values, say theta equals alpha and theta equals beta. And then who knows what the region's bounded by, but it's just this flag-shaped thing. And so in this problem, our region is here. So we fill all this in. It's just a flat region in the xy plane like any other on any other double integral problem. But our description of the region is what will be different. So we fill it in. That's the region. And we want to think about how to break up this region into lots and lots of little subregions that will serve as the base of our columns that go from the xy plane up to the surface. And in the past, we've been using little tiny subrectangles. Now, we're going to use little tiny polar sub-areas. So imagine breaking up the region like that instead of into perfect rectangles, and focus your attention specifically on this piece. So that's one of the tiny pieces. It corresponds to some tiny change in theta and to some tiny change in r. So I'm going to draw that one piece much bigger now so we can focus on just it. So that one red piece maybe looks like this. So we're blowing it up big, so now it looks like this. So there's that one little piece, and we'll shade that in just so we can see it nice and big. Now think about the relationship between r and theta and this region, which is just one of gazillions of tiny subregions in the original region R. So this dimension here, this corresponds to a tiny change in radius, so a tiny change in distance to the origin. So back here on this picture, that's right here. And then there's a tiny change in theta, which back here on this picture you might call delta theta. In there, some tiny change in theta. On this picture, on the blown up version, you can hardly see it. But these lines will eventually meet down at the origin, And so this is some sort of tiny change in theta, like this. And we're interested then in what's the tiny change in area. What is this area contribution delta A? Now, the beauty of this is you guys have studied polar coordinates in Calc 3. And so you know that the area of a sector, like if this was R1, say, and then this was R2 in terms of distance to the origin, the area of the pizza slice all the way out to crust at R2 is 1/2 R2 squared delta theta, and then we take away the pizza slice with crust at R1. So take away 1/2 R1 squared delta theta, and that's our delta A. Okay, now let's simplify this. Factor out the 1/2, and then you got R2 squared minus R1 squared, and then you got delta theta at the end. But R2 squared minus R1 squared factors, write that as R2 plus R1 times R2 minus R1 times delta theta. Write that as R2 plus R1 all over 2. And then R2 minus R1, that is delta R. Now, here's the thing. If you're going to formulate the double integral using these tiny little subpolar regions, then you're imagining it happening as delta theta goes to 0, so you're taking tinier and tinier angle slivers, and as delta R goes to 0, so tinier and tinier differences in R's, and you just cram in more and more and more of these little regions in there. Here's the thing. In that limiting process, the R2 and the R1, this disparity right here, delta R is going to 0, and delta theta is going to 0. Well, if delta R is going to 0, then that means R1 and R2 are approaching one another. And so this is an average here of two quantities, R2 and R1, that are getting closer and closer. And if you average two things that are very close together, you just get either one of them. Essentially, the point is this. As number of polar subregions grows large, delta A approaches R dr d theta, and this thing serves as our dA. So that's a heuristic argument as to why in polar dA in our polar double integrals is R dr d theta. Whereas in rectangular, the dA, that's easy because every little subregion is an actual rectangle that's delta x by delta y. So in rectangular, dA is just dx dy. In polar, dA is not simply dr d theta. There's this extra factor out in front that comes from the polar geometry. So dA is r dr d theta. Think it like a pirate would. Ardy theta. I embarrass myself for you guys. But remember it. Remember the pirate. Don't forget this piece here. It's rd theta, not simply drd theta. Now, if you believe in that, and you can describe polar regions, then you're ready to do polar integrals. So let's set up one example that really is striking in the fact that I think it would be quite hard and or impossible to do in rectangular coordinates. So here's an example. Compute the double integral over the region R of e to the x squared plus y squared with respect to area, where R is, here's the region we're trying to do. This is good old xy plane. The region is this. It's a quarter circle. So this is our region. And we're going to choose to describe it however we like. Radius is 1. That's playing the role of R. So you could describe that region in rectangular coordinates as x varying from 0 to 1, y varying from 0 up to root 1 minus x squared. After all, the edge of this is governed by equation x squared plus y squared equals 1. But that region is much better described in polar. Moreover, suppose you were insistent on Cartesian coordinates. You said, no, I don't like this new polar stuff. I'm just going to do it Cartesian. It's fine. It's fine. I'll do it Cartesian. Okay, well, if you're going to do it Cartesian, this would be dx dy in Cartesian. And think about the inside integral. If you were going to turn this into a double integral, you would have to integrate e to the x squared plus y squared dx, or e to the x squared plus y squared dy. To which I say, good luck. It's not happening. There is no way we're integrating e to the x squared plus y squared dx. On the other hand, if you were to turn this into polar, the magic happens. In polar, the double integral over that region R of the function e raised to the x squared plus y squared with respect to area becomes an iterated integral. The dA becomes r dr d theta. One more time, r dr d theta. Don't forget the r. That means the inside integral is being done with respect to r, and the outside integral is being done with respect to theta. Look back at this picture here. What kinds of thetas are in play? 0 to pi over 2, clearly. For each of those thetas, between 0 and pi over 2, what kind of r's are in play? 0 to 1, clearly. We're integrating e to the x squared plus y squared. What is x squared plus y squared in polar? Nothing other than r squared. Now look at the inside integral. That is primed and ready for a nice, easy u substitution. Let u equal r squared. The du is just waiting for you, and you are off and running. I'm going to have you guys finish the job on that integral, but it really does illustrate that on some problems you would much rather integrate with respect to r and theta at the expense of dA becoming r dr d theta, then you would want to integrate with respect to x and y. So you guys finish the job here. Integral is straightforward. That's why you want to know polar. All right. Have a look at those suggested problems. Come to class with questions on Tuesday. I'll see you next time.